Hey everyone, I'm Suha. I'm an undergrad CS major at Georgia Tech and a security engineering intern at Trail of Bits. This summer, I worked on Privacy Raven, a comprehensive privacy testing suite for deep learning. Essentially, I built a Python library optimized for usability and efficiency that allows users to simulate privacy attacks on any deep learning system. So your first question might be, what do privacy attacks on deep learning even look like? Imagine that you're tasked with securing this medical diagnosis system on the right. Right away, you're aware you have a very important job on your hands. Medical privacy is an extremely critical requirement bound by multiple regulations, and for a very good reason. After all, patients need to be able to trust their doctors and their hospitals with sensitive info. Any major vulnerabilities here undermine the existence of these automated systems themselves. As you can see in the diagram, in this system, users determine if a patient has a brain bleed by sending in an image and receiving a yes or a no answer. The users are given as little access to the deep learning model as possible. Therefore, you may be inclined to believe that there's not much an adversary can actually learn about the system. Let's see what an adversary simulated by Privacy Raven is capable of, even when strongly restricted. The adversary first launched a model extraction attack to create a knockoff, stealing the intellectual property of the medical diagnosis system. They were also able to reconstruct images from and even re-identify patients inside of the training dataset through what is known as a model inversion and a membership inference attack, respectively. Once again, they were able to do this when only receiving a simple yes or a no from the system, and they used less than 15 lines of Python for each attack. I'll cover each of these classes of attacks one by one later, but most importantly, you just found some serious HIPAA and GDPR violations with the system at the very least. So why does this happen? The reason these systems have become so popular is because they enable software to perform tasks without explicit programming. However, this capability means that deep learning is more vulnerable to attacks on privacy and security. Right now, these systems lack comprehensive assurance tools like fuzzing and static analysis, in contrast to other forms of software. Privacy Raven is a first step in this direction. It specifically focuses on assurance for attacks that target the intellectual property of the model and the confidentiality of the training dataset. Presently, the attacks provided by Privacy Raven use the strongest possible threat model. In other words, the adversary only receives labels from an API that queries the deep learning model. A weaker threat model might be white box access, where the adversary can access info about the target, like model parameters or loss gradients. Some black box attacks also assume that the adversary receives full confidence predictions. But by operating in the most restrictive setting for an adversary, Privacy Raven can analyze the worst case scenarios. This tool is designed to be used by a wide range of people. This could potentially include a security engineer analyzing the susceptibility of their bot detection software to privacy attacks, a machine learning researcher evaluating different types of privacy-preserving machine learning techniques, or developing novel privacy metrics and attacks, or a privacy engineer building an auditing tool for data provenance by repurposing membership inference attacks. So first, let's take a look at model extraction attacks. Model extraction is what enabled the simulated adversary to create a knockoff version of the target. This is formally known as extracting a substitute model. The motivations behind model extraction tend to fall into two categories. Adversaries that launch attacks optimizing for high accuracy are usually financially motivated. Having a substitute model means that they can avoid paying for the target in the future, and they can profit off of their own version. Meanwhile, adversaries optimizing for high fidelity want to learn more about the target. The substitute model extended using this attack allows the adversary to then launch other classes of attacks, such as adversarial patches or model inversion. The different methods of model extraction found in the literature sometimes take wildly disparate approaches, which leads to other tools and implementations treating each extraction attack distinctly. Instead, while building Privacy Raven, I partitioned model extraction into multiple phases that encompass most attacks found in the literature. The diagram shown here is a very high-level overview. The repository contains a much more fine-grained analysis of this attack. First, some synthetic data is generated. Then a preliminary substitute model is trained upon that dataset. Then the model is optionally retrained using a subset sampling strategy for performance optimization. This modular approach means that users can quickly switch between different synthesizers, sampling strategies, and other features without being limited to configurations that have already been tested and presented. For example, a user can easily combine a synthesizer found in one paper with a subset sampling strategy found in yet another. Here's how you would launch a model extraction attack in Privacy Raven in less than 15 lines of code. I removed the import statements due to space constraints, but the full example is inside of the code base. In this first part, a query function is created for a PyTorch Lightning model included within the library. This part would vary depending on the system structure. I made sure to include several target models in Privacy Raven in order to accelerate user prototyping. This one right here is a standard fully connected neural net trained on MNIST. Next, the eMNIST, or the extended MNIST dataset, is obtained in order to see the attack. The bulk of this attack is contained within this final portion. Here, the knockoff synthesizer is used to train the ImageNet transfer learning classifier. These other classes of attacks can be launched in a very similar fashion. Now, the output of this attack would take at least 10 minutes to generate. So instead of showing you the whole output, I'll briefly explain what's contained inside of it. First, Privacy Raven will show you statistics about the target model. Then it would provide details about the synthetic dataset and the resulting substitute model, including training progress and efficiency metrics. Finally, it would display measurements for the accuracy and the fidelity of the substitute model, and in turn, the model extraction attack. Now let's learn about our second class of attacks, membership inference. Going back to the example of the medical diagnosis system, the creation of that software relied upon many patients being willing to trust the developers with their private medical data. If a patient's participation, and in conjunction with that, their image and diagnosis could be recovered, it would first of all violate HIPAA, and then it would diminish the trustworthiness of the whole enterprise. Membership inference attacks are, at their core, re-identification attacks that achieve precisely that. The success of these attacks are dependent on certain qualities of the training data distribution, meaning they're less reliable than model extraction. Privacy Raven is actually one of the first implementations of these attacks under the defined threat model. Before delving into the attack framework, I want to talk about adversarial robustness, which is a measure of resistance to adversarial attacks. One of these attacks is displayed here on the left. So look at these two panda images. Do you notice any differences? This noisy image in the middle was added to the first picture to create the second. This difference is imperceptible to humans, but it caused an image classifier to misclassify the second image as a capuchin instead of a panda, with a very high confidence. While Privacy Raven doesn't aim to defend against these adversarial attacks, adversarial robustness is a key concept for deep learning privacy and is integral to the construction of membership inference attacks. As with model extraction, I adopted a phase-based approach to this attack, of which a high-level version is displayed on the right. The actual attack is performed by what is known as an attack network, a binary classifier that determines whether or not a data point is inside of the target training dataset. So the dataset for this model comes from combining adversarial robustness calculations with the outputs of a substitute model generated from an extraction attack. The technical details of this dataset creation is unimportant at the moment. What is important to note is that, unlike other tools, Privacy Raven integrates the extraction API, making it much, much easier to optimize this first phase to achieve better performing attacks and ultimately stronger privacy guarantees. Onto our final attack, model inversion. This class of attacks is a much more nebulous area of work, which means we couldn't adopt a similar all-encompassing phase-based approach. What a model inversion attack does is that it looks for data that the target has memorized. In the medical diagnosis system, this was a reconstruction of the images the target was trained upon. This image here on the right shows the results of a model inversion attack on a facial recognition system. As with membership inference, the inversion API integrates the extraction API. so users can once again benefit from customizable and optimizable extraction. In the defined setting, these attacks actually function by training a neural net to act as the inverse of the original model. Technical details related to that are beyond scope, but are covered further in the repository and a couple of other places. Before I finish this talk, I'd like to briefly mention some Privacy Raven features still in incubation. In addition to adding more methods for the previous classes of attacks, we're working on a new interface for metrics visualization that prioritizes clarity, as well as automated hyperparameter optimization for more coverage and stronger privacy guarantees. We're also working on the verification of differential privacy mechanisms and privacy metric calculations. More classes of attacks, including ones that specifically target federated learning and generative models, as well as property inference and side channel attacks, will be incorporated into Privacy Raven in the future. Finally, we're planning on adding models that have already implemented privacy-preserving machine learning techniques, such as secure multi-party computation. Privacy Raven will be released to the public soon. I'll also be talking about this tool at the Open Mind Privacy Conference and the DEF CON AI Village Journal Club in September, so be on the lookout for that. For more information, feel free to contact me or my mentor Jim at these emails. Thank you all for your time.